Good evening, good evening, good evening, minions. This topic was requested by so many of you, and it's not just about the request. In fact, there were so many questions in the February attempt that came from this chapter as well as modern physics. So, listening to all of you, just like we always do, today we are going to discuss semiconductors, transistors, diodes, logic gates. Also, I'm going to make you solve some really conceptual questions on semiconductors and also make you understand what exactly is the basics of this so that you have some idea about it. So when you go back and study from your textbook after this lecture, you will definitely feel confident about this chapter. And we have also included a lot of PYQs in this session. So get ready because this is a marathon session and this silicon atom is going to play a very, very important role today. So all this with me, Shreyas Sir, Master Teacher for Physics at Vedantu, going live. Hello Sumanjali, Lohitraj, Yalini, Shruti, Anu, Minyanarthi, Sumanjali, welcome Vijay, welcome Shubhana, welcome Luffy Monkey D. Wow. And Shreyas Sir's minion is also here. Hello everyone. Hi, good evening Nancy, good evening everyone. Yes, Anu is very excited, even I am excited. Hello Rox, Satvik, hello Yukta, hello Priyal, hello NVD, welcome aboard, hello Xtech, hello Empire, hello Sashi, hello Aditya, welcome, nice to see all of you. Chaitanya, hello Doctor. So very, very important chapter, and those of you who do not know me, this is Shreyas here and I have been teaching for almost a decade, producing amazing results that you can see on the screen, and I really hope that this batch which is going to pass out this year is also going to rock it. You're going to nail it and you're going to not just get good ranks but also going to get good colleges, all thanks to We Enthuse, which is very, very dedicated English medium channel for JEE aspirants, for engineering entrance aspirants, and for all those aspirants who want to crack any other competitive exams out there. Good evening everyone. Hello Avinash, hello Mona, hi Vijay. Nice to see every one of you. Keep the chat box rocking, and if you want to get in touch with me, here is my Instagram handle, Shreyas_Vedantu. You can definitely ping me over there, and I have slowly reduced my backlogs. Whenever I try to reduce my backlogs of messages, again a new backlog comes in, so I'm trying to answer as many queries as possible. Okay, so you can follow me over there, you can get your queries answered, and also I'm going to post a very cool video on center of gravity tomorrow or by tonight, so keep a track of it. Hello Asmi, nice to see you. Alright, and I hope you have already smashed that like button out there. Go ahead, if you have not done it yet, please do that. Yes, that will show your love and your support for this channel and towards me, and all of this is being done for free. And one more thing, if you are new, do not forget to hit the subscribe button. Very easy, just become a subscriber so that you do not miss any new chapter, update, any other important message that we would love to convey to you. Alright, so let's get going without any further delay. And let me also tell you that this week we have done a lot of topics. In case you have missed center of mass 0 to hero session, please watch it in our past videos. 0 to hero of center of mass, we conducted a mock test. Then in case you missed communication systems, I did it on Thursday guys, that is yesterday. Please check out the past video in detail lecture on everything about communication systems with simulations and all the other formulas with derivations as well. So please do check it out. There are problems also included in these sessions. Today we are doing 0 to hero in semiconductors. Tonight 11 o'clock 0 to hero in collisions, momentum and impulse. Do not forget, it's not at 10 o'clock, it's at 11 o'clock, 11 to 12, one short series. This one is a marathon session, and tomorrow rigid body dynamics 0 to hero session on rotational mechanics out there. So a lot of amazing sessions lined up for you. Thank you. Chaitanya, don't worry, we'll come up with all kinds of lectures for everything, don't worry. Yes. First, I'm going to cover all the high frequency chapters for March attempt, and once the March attempt is over, then we'll also do the other chapters. So first, let's focus on the high frequency chapters. And in case you are wondering what are those high frequency chapters, just check out the round table conference which we did, which includes all the list of the important topics to score minimum 50 plus in every subject. and those are very, very vital topics. So we are going to do them first. Nice to see you, all of you. Well, Dinesh, we are conducting all the classes in the evening only. Yes, so most of the students get free by around 4 o'clock, 5 o'clock, whatever practical exams, etc. Good evening, Matsalya. Hello, Shabana. Hello, Naga. Good evening. Good evening. Good evening. All right. So, Manju Nad, magnetism will be covered next week. Okay, cool. Let's get going. So, for all the important updates, PDFs, formulas, everything, notes, etc., please join the Telegram group. Where is the link for the Telegram group? It's in the description box below. Join it so that you will not miss any update. So please join it. Very important. All the PDFs, all the formulas, everything will be given to you on Telegram group, PDF form. You can download it. Okay, so let's get going. Let's get started. Now, to make you understand what exactly is the difference between semiconductor, conductor and insulator, I have taken a very simple example of sodium atom. And that's what even H.C. Verma does to make you understand this. In fact, I would suggest to read this chapter, please refer to H.C. Verma. Study this chapter from H.C. Verma. Alright. So study this chapter from H.C. Verma. Very important chapter. Very, very nicely he has explained all the concepts beautifully, and I'm pretty sure you'll understand it even better because you will attend this class, because I'm going to relate, or I'm going to take the examples or his examples out here, so that theory wise, but problems wise I'm going to use PYQs, so that you are going to easily correlate the theory from H.C. Verma and whatever I'm going to teach. So that's very important. Okay, now in a sodium atom, right, atomic number 11, let's think about how the energy level diagram looks like. Hello Shreya, welcome, join in Harry Parker. All right, yes, okay, even I'm thinking, how about guys, will you like me giving you underlined notes of this chapter from H.C. Verma? My own underlined notes from H.C. Verma, would you love it? What say guys? Let me know. Let me know in the chat box, would you love it from the Telegram group? Do you want it or do you don't want it? If you don't want it, let me know. Yes, no. For this chapter, because this is a theoretical chapter. See, other chapters, there is nothing to underline. Very important chapter. So how about underlining all the important pointers from H.C. Verma and giving it to you? Yeah. So you need to join the Telegram group. I'll give the underlined notes of this chapter. Very important. Very good. One promise you need to do. Okay. One thing you need to do. Do not forget to hit the like button and do not forget to hit the subscribe button and share this video. Yes, share this video with your friends. If you're going to do that, then I promise that I'm going to put up my notes on Telegram. Yes, you need to do that. Okay, very good. Excellent. Chalo. Now, how will the energy level diagram look like? Let's see how the energy level diagram will look like. So, this is how it will look like. 1s has 2 electrons. Everybody knows this. 2s has 2 electrons. 2p has 6 electrons. Whereas, because the atomic number is 11, the third s orbital has only 1 electron. I feel there is one vacancy over here. Alright, you can see there is clear cut. There is one vacancy. Alright, there is a vacant place over here. And if you talk about the 3p orbital, well, that's completely vacant. Alright, that 3p orbital is completely vacant. Correct, guys? So, this is how the energy level diagram looks like for one sodium atom. Now, think about it. Okay, everybody is understanding, I'm guessing. This is very simple. This is low energy, high energy, high energy, high energy, high energy, and so on and so forth. Now, if I take many sodium atoms far away from each other, they are all far away from each other, each sodium atom will have a similar energy level. For example, there is a sodium atom here. It has some energy level diagram like this. This is very important for you to understand semiconductors, so pay close attention to whatever I am saying. Another sodium atom somewhere else, non-interactive with the previous one, will also have a similar energy level diagram. Another sodium atom somewhere else will also have a similar energy diagram. They all have similar energy diagrams. They are not interacting with each other. They have not yet formed a bond. They are not yet part of a solid. Understand this. Now, what happens if they come close to each other? That's my next question for you. So what happens if they interact? What if they are part of a solid? What if they interact? Then there is a small change. See, when they form bonds, these energy level diagrams get changed little bit. So if this atom interacts with this atom, this 1s will interact with this 1s. This 1s will also interact with this 1s of another atom. Similarly, 2s will interact with 2s, 2s will interact with 2s, and you will get new energy levels. So what you are going to see is the 1s of this atom will interact, and you will get two new energy levels. If 3 atoms interact, you will get 3 new energy levels for 1s. Similarly, 2s of this, 2s of this, and 2s of this. If 3 atoms interact, you will see 3 new energy levels being formed because of these 3 atoms. And similarly for the 3s of the outermost shell. So each orbital will have some, or each atom's electron will have some energy. When they interact, one will go down, one will go up. If 3 of them interact, one will go up, one will go down, one will go down. I don't know, something will happen. But you will get 3 distinct lines for that particular orbital. If 4 of them interact, then 4 lines will interact. One will go up, one will go down, one will go up, one will go down, and you'll have 4 lines for that orbital. I hope that is clear. Yes, sharing is caring kind of a thing. They form a new kind of molecular orbital. You can think of it. It's a new kind of energy level diagram. So if one atom is there, you have only one line. If 2 atoms are there, that 1s orbital will have 2 lines. If there are 3 atoms, there will be 3 lines. If there are n atoms, how many lines will be there? Come on, minions. Let me know in the chat box. Let me see if you are alive or dead, or are you a zombie? Come on. If there are n atoms interacting with each other, then each orbital will have how many lines? Each orbital will have how many lines? So just one, basically, individual atoms have discrete lines. 1s orbital, 2s orbital, 2p orbital have one line energy level diagram. But when they interact, then they form new energy levels, and the 1s of one and the 1s of the other will interact, and they will go up and down. Yes, there will be n number of lines for each orbital if n atoms interact with each other. Similarly, if 1 mole of atoms interact with each other, then it will be 6 into 10 to the power 23 lines. How so many lines? I don't think you will be able to see it. Very good, minions. Excellent. You have answered it correctly. Some of you answered infinite. Some of you also said zombie. I was glad that we have zombies also in the class. Welcome, zombies. Those are the new breed of people who are attending VNQs. Yes, excellent. So if you have so many lines, they are so close to each other, they are hardly distinguishable from each other. Once they have so many lines, all right, they look something like this. Look at that. They look something like this. Imagine this is the blue one is 1s. Imagine the green one. Okay, just imagine this blue one is, let's say, from 1s. Imagine the green one is from 2s. Imagine the red one is from 2p. Imagine just. So you will see when number of atoms interact, they will keep on increasing, and sometimes they might also overlap with each other. I hope you can see that. They can also overlap with each other because each one of them is spreading. So they can overlap or may not overlap, depends from atom to atom. So this is what is going to happen. And this collection of these lines, what is it going to be called? What will I call this collection of these lines? Come on, minions, answer in the chat box if you know it. Come on, before I show you the next slide, what do you think is this collection of these lines going to be called? Hello, Funny Teja. Yes, Anu. Very good, Sashi. Very good, Gopala. It's a band. Continuous lines almost. Yes. So bands can be thought of as the collection of individual energy levels of electrons surrounding the atom. So this is one band. This is another band. This is another band. So this is collection of energy levels of electrons surrounding each atom. Excellent. Very good, minions. You're slowly getting the idea what we are coming to. Now, don't worry, all these notes will be available to you. I hope simultaneously you're writing down whatever important things I'm telling. Very good. Now, I can give you an example. Again, let's take the example of sodium. Sodium has 1s. It has 2 electrons. 2s also, it has 2 electrons. 2p, it has all the 6 electrons. 3s, it has only 1 electron. So imagine if I draw the band of a sodium atom, sodium atoms in a solid, a collective solid, the energy band, I feel the 3s band will be half filled. Do you understand this? Why it is half filled? This one will be half filled, or it is half vacant. This one is completely vacant. All these are completely filled because of electrons. So this is half filled or it is half vacant. I hope this is clear. Excellent. Now, don't worry about Fermi levels, Omkar, all that things are not there. You are not going to study so much in detail. Just understand the application of semiconductors. That's why you are here and that's what is there in JEE Mains. Don't mess up your head. Alright, if somebody is teaching you, they're just trying to play with your mind. Alright, now what I want you to understand is, look at the sizes of these bands. Oops, 1 second. Look at the sizes of these bands. Do you see this kind of question can come in JEE Mains? Note it down. Note it down. 1s band has smaller size, 2s band has slightly more, 2p has slightly more, 3s has slightly more, 3p has even more. Why is the band size increasing? Reason is, when two atoms interact, their innermost shells can hardly interact with each other. So 1s and 1s of two atoms can hardly interact, and their one going up and one going down will hardly be anything. They will hardly have any difference. But the outermost shells, they are highly probable. They will touch each other. They can interact. They can mingle with each other. They are not protected. They are not screened. That means when they interact, then the spread of those lines will be higher. That's why those bands have higher width. Very, very important pointer out there. Yes. Is this clear? Just one, don't ask those questions because it is not relevant. Again, you are getting into some another topic. All right. Yes, Anu, we are going to study transistors. Very good. So understand whatever I am telling you. Only that is important. Everything else is bakwas. You don't need to study all those things. Anshu Arli, just replay the part. We are just begun, just 5-10 minutes back. You can replay at 2x speed and catch up. All right. Now, if this much is clear, I want you to understand that these bands over here, alright, these bands over here have a special name, and the bands on the top, which are half filled or not filled, have a special name. Why do they have a special name? Let's come to that. These bands which are completely filled, do you know what is it called? What is it called? Yes, what do you think is this called? Yes, what is this called? What are these lower bands called? Adyasha, we are doing all the chapters like this. Adyasha already have started Zero to Hero series exactly for the same. Yes, come on, think about it. Come on, think about it. Yes, this is called valence bands. And the ones which are not filled, they are called conduction bands. Why are these called as conduction bands? Very simple. When you take silicon atoms like this, or sodium atoms like this, or any atom like that, if you apply potential difference, meaning battery, if you connect a battery, what will happen? Which electrons will jump? Which electrons will jump and start flowing? The ones here or the ones here? Come on, answer this question. If I start applying potential difference, do you think that the 1s electrons will start flowing, or do you think the 3s electrons will start flowing? Think about it. Yes, the outermost one, the 3s one, the conduction band. So these electrons, that's why are called conduction electrons, or this band is called as conduction band, because the electrons in these bands take part in the conduction of electricity. These are not so cooperative. They are very boring people. They hardly interact. They are extroverts. Oh, sorry, they are introverts, my bad. They are introverts. They will not mingle around so much because they are inside their cocoon. They are in the innermost shells. They're like, okay, I don't want to interact with anyone. These people are extroverts. The moment they see a battery, hey, let's go. There is a battery. There is a potential difference. Let's move. So these are free electrons. These are extroverts. They mingle around. The band energy is also very huge. Yes. So coming to that, the lower ones, the ones which are occupied, they are called valence bands. The ones which are unoccupied or partially filled, they are called as conduction bands. Very good. Yes. Yes, Gopala, the ones inside are not minions. They are intrions. They are viruses. And the ones, the minions out here, they are, I'm pretty sure, in the conduction band out there. Excellent, Gopala. Okay, so conduction band is the lower range of vacant electron states. So these are the vacant states. Valence band, these are the filled ones. All right, they are the highest range of electron energies in which the electrons are normally present. All right, all this is at absolute zero. What is the significance of zero temperature? I'll come to it in a bit. Yes, don't worry. Very good, Samla, very good, Princey, very good. Excellente. And the gap between, this is very important, note it down, band gap. What is band gap? From here to here, from here to here, from here to here. The band gap is the gap of energy between the lowermost conduction band and the uppermost valence band. Very important. So band gap is the distance between the valence band of electrons and the conduction band. So this is called as the band gap. I hope this is clear. This is called as the band gap. Now you can understand probably what is the significance of this band gap. Just imagine, this is the band in which if the electrons are present, the conduction band, when the conduction happens. This is the band in which if the electrons are present, the conduction does not happen. Now, if the electrons are here, they are not conducting, and if this band gap is huge, then don't you see that it needs lot of energy to jump into the conduction band? Don't you see, if this band gap is huge, the electrons here to go into the conduction band will need lot of energy. So that means you need a very strong, powerful battery for the conduction to begin. I hope this is clear. Achut, don't spam. Alright, excellent. Similarly, if this band gap is zero or negligible, or what if the conduction band overlaps with the valence band? What will happen if the conduction band overlaps with the valence band? If it overlaps, that is like the best thing. If it overlaps, the electrons which are already in the valence band, they can easily go into the conduction band. It will be so easy for them to conduct. Hardly any electricity, and they will start flowing into the conduction zone. Excellent. So these are very important definitions. I have written it down for all of you. All the minions, don't worry, I have written down all the important theory pointers. And if you find something important which I say, do not forget, you have to also make notes simultaneously. Excellent, Nancy. Now comes the role of the temperature. Now let me tell you the role of the temperature. Now whenever you draw these energy level diagrams, this one or this one, please remember one very important thing which nobody tells you so easily. All these bands are always drawn at, keep this in mind, they are always drawn at 0 Kelvin. 0 Kelvin, keep this in mind. Very important. Lowermost temperature. Welcome Rupak, you are at the right place at the right time. In fact, we are doing 0 to hero series for all the JEE aspirants, for all the competitive exam aspirants, so that we complete all the important chapters in this small span of time. Alright, yes. That means if an electron is here, it has two ways to go to conduction band. Think about it. It has two ways to go into the conduction band. One is you apply potential difference, you connect a battery, and this battery will pull these electrons into the conduction band. It will suck because of that potential difference. That's option number one. What is option number two? Can you guess what is the option number two? Think about it. Modit, that is not necessary. Again, you are deviating. Hai na? Alright. What do you think? Welcome Bhavani to this channel. Nancy, it's not needed. It's not needed. It's not there in syllabus. You're just wasting your time. Again, Nancy. Yes. Yeah, at 0 Kelvin means the lowermost temperature. Okay, it is at the lowermost energy level. Yes, by providing energy, by providing temperature. So this is tending to 0 temperature. When you increase the temperature, the electrons will collide with each other. There will be thermal collisions, and then they can get knocked out to higher energies, or they can get excited. So then in the conduction band, there can be more number of electrons, just like this simulation shows you. So going to that simulation out here, look at this. So if you supply energy, the electrons will go to higher energy level and they can go into a conduction band. After some time, some other electron might again come back, but yes, you are constantly supplying energy. So if you constantly are heating it, or there is a temperature which is maintained, there will always be some push given to the electron to go to higher energy state, and there will be always some electrons which will again get low on glucose, low on energy, low on motivation, and again come back, and you again need to give it some dose so that it again gets excited to higher energy levels. I hope this is clear. Excellente, excellente, very good. So temperature also can make the electrons move to a higher energy level, and in fact Yes, it's like a cyclic process. Thank you, Prashant. Excellent. Excellent. Now, welcome, Sarma, to the new channel, to our channel out there. Okay, now this decides whether something is conductor, semiconductor, or insulator. So, three things. Feel is coming, very good. So, it is basically, this is what will decide whether it's a semiconductor, insulator, or conductor. Look at this. Guys, this is all at 0 Kelvin. What is this at? All at 0 Kelvin. So let me be very clear about it. So this is at 0 Kelvin. Alright, this is hypothetical. You can never reach it. But this is understood. At 0 Kelvin, it will be at the lowermost energy levels. The valence band and the conduction band, if this gap is very large, if this gap is very huge, then it will become an insulator. Because you need to give it lot of energy either via temperature or via potential difference for it to jump from here to here. So even at room temperature, the electrons cannot overcome this band gap. That's why this is called as an insulator. This is called as an insulator because the electrons are unable to jump even because of the temperature which is provided even during our normal temperatures around us. So that's why it's an insulator. Next up, imagine this. If the gap is less, such that this gap is almost such that, at room temperature, most of the electrons from valence band can easily jump into the conduction band just because of thermal energy. Just because of thermal energy, the electrons from here can easily jump into the conduction band because of thermal energy at room temperature. Then what will happen is that even if you apply a normal potential difference, the electrons in this conduction band will start conducting. But there are not too many electrons. Few electrons which jump can easily conduct electricity. That's why it's called as a semiconductor. Alright, so a semiconductor is nothing but when the band gap is very small, alright, and at using the thermal energy, the electrons can jump from the valence band to the conduction band. Amazing. Now, EG is yes, the band gap. Yes, yes. Now, imagine a situation where this band and this band coincide with each other or they overlap. I would say you don't even need the thermal energy. You don't need that room temperature. You don't need to heat it. Even at 0 Kelvin, understand these electrons can easily join in over here and they can conduct electricity even at very low temperatures. Unlike this. See, this one at low temperatures will not conduct electricity because it won't have sufficient energy to jump. So that's why these are called as conductors. I hope this is clear. Very good. Yes, Ashish, we are going to discuss everything. Dorabuji, if you are late, and all the minions, all the V enthusiasts who are late, do not worry, you can always replay back. I would advise you, because we have just completed some 15 minutes or 20 minutes, just replay back and catch up at 2x speed and reach here and try to attend the session completely live, which is very important so that you will get the feel of this chapter. Very good. Just like you have been attending every other chapter, attend this lecture. I am going to touch everything today: Zener Diode, diodes, semiconductors, PN junction, rectifiers, transistors, logic gates, everything in this marathon session. It's a marathon session. It's a long session, at least till 9 o'clock. Yes. All right. Very good. Yes. Yes, Dinesh. In fact, we have questions based on this now. Let's see how many of you can answer this question. Yes, today is a marathon session. The lecture is going to be till 9 o'clock. Come on. Very good, Devki. We can and we will. Excellent. I was seeing all your comments which you posted on that motivational session I gave you on how to score more than 180 plus in the upcoming JEE Mains. I'm really happy to see all your comments out there, and really I would love to congratulate all of you for showing so much of courage out there. Come on. A lot of you are saying C. Very few people like Astha and I think somebody like Bhavani said A. Most of you are saying C, 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 C. Okay. So silicon, Si, is a semiconductor. Very important. So at absolute zero, a silicon is an example of a semiconductor, guys. What will happen? Will it behave like a non-metal, metal, insulator, or none of these? Come on. Yes, the answer is insulator. Very good. Excellent. Excellent. And the reason is, Remember, there is already some energy gap between the conduction band and the valence band, right? I just gave you for what is this? Semiconductor. There is already some gap. So at very low temperatures, how will you overcome this gap? You need to apply tremendous electricity to overcome that gap. So it will behave like an insulator. Only at room temperature, it will start conducting. Yes, that is the answer. Very important. A lot of people mess this up. They think, oh, silicon is a semiconductor. So if it is a semiconductor, then it should be none of these. A lot of people feel that it should be none of these, or it should not be a metal or something like that. That's wrong. Okay, very good. Cool. Next question coming up on your screen. The conduction band and the valence band in a good conductor are well separated by a forbidden band, are overlapped, sometimes overlap and sometimes separated, or have forbidden band. Come on, think about it. Let's see how many of you get this. Anu says B, Tejas says B. Come on, minions. I really want you to ace this. I'm going to make you practice so many questions today. After today, you are going to feel like a hero. And you are going to comment that I felt like a hero after today's session. Let's see how many of you are going to do that. Very good. Many of you are saying B. Excelente. Oops, I went to the next question. My bad. Yeah, it is overlap. A conduction band and valence band for a good conductor. What will happen? Conduction band and valence band, they will overlap. The electrons will easily enter into this zone and they will easily conduct. So that is a very good conductor. There is no band gap. In fact, it is overlapping. That is the best way of conducting or having the best conductor in this world out there. All right, cool, great, amazing. Next question. A strip of copper and another is germanium. All right, now copper is a conductor. That's your hint. And germanium, come on, think what is germanium. You should know what it is. Alright, I am not going to tell you. Come on, it's simple. Are cooled from room temperature, which is close to 300 Kelvin, from 300 Kelvin to 80 Kelvin. So it's cooled. Then the resistance will, what will happen? Come on, think about it. What will happen to the Sahitya? Yes, I'll reply beta. Hold on. Sometimes it's not so easy for me to reply to every comment. I have to reply on Instagram. I have to reply on comments. I have to take my classes. I have to do a lot of things, so usually it takes few days for me to reply. Hold on, don't worry, I'm going to reply. Okay, we have Shreyas Sir minion saying C, Shabana saying C, Neha Fatima saying B. All right, Anu Peter saying C, Shubham saying C, I guess. All right. Okay, well, the correct answer is C. Copper is a metal. Germanium is a semiconductor. Now, think what will happen. Think what will happen when you cool something. Think what will happen when you cool it. The copper, which is a conductor, the resistance will decrease. Why will the resistance decrease? Because copper is already a conductor. Already the electrons are in the conduction band. Now, for conductors, very important thing, write it down. This has come several times in JEE. For a conductor, when you increase the temperature, what will happen? The collisions will increase. Tuck, 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 tuck. So many electrons are there already. They're crowding the conduction band. So when you increase the temperature, their collisions will increase. So what will happen to the resistance? Obviously, resistance will also increase. Understood? So resistance will increase when you heat a conductor. So when you cool it, resistance will decrease. So for copper, the resistance will decrease. Is that clear? All right. I hope this is clear. Okay, Saitam, I would not have liked it. Somebody else would have liked it, like the channel manager or somebody. So I will sit and reply. Okay, don't worry. Great. But for a semiconductor, when you heat it, then the electrons from the valence band enter the conduction band. When you heat a semiconductor, the electrons from the valence band enter the conduction band, and they are only responsible for conduction. So obviously, if you cool it, the electrons which are jumping will no longer jump. There will be very few electrons in the conduction band. If there are few electrons in the conduction band, conductivity will go down, resistance will go up. So that's why germanium, it increases. Is that clear? Very good. No, the answer is not B, Asta. Yes, be careful. See, it is cooled, it is not heated. If the answer was heated, then it would be option B. The question is, it is cooled. Be careful. I hope this is clear. Is that understood? Excellent. Very good, very good, very good. Clear, clear. Sarma says clear. Minarati says clear. Oh, Asta says okay. Dora Bauji says yes. My God, Dora Bhuji is such a nice name. You remind me of bhujia, that aloo bhujia, Haldiram's aloo bhujia. Such nice aloo bhujiyas they make. You remind me of that. Anyways, all right. Next question. In a semiconductor, the separation between conduction band and valence band is of the order of. Come on, let's see. Ramagor, you can replay back the session little bit and you can watch it again and come back. All right? Okay. Come on, Tejas says C. Wow, distilled water clear. Thank you, Princey. Okay. Yash also saying C. Priyal saying B. Naresh saying D. Monkey saying B. Wow. Aishwarya saying C. Gopala Joshi saying B. All right. Okay, Asta is waiting for logic gates. Hold on. Revise everything, Asta. Everything is important. Just don't, haste this process. Yeah, just be patient a little bit. Okay. So I'll tell you what. This is a theory-based question. You should know this value. The band gap is of the order of 1 electron volt. You should know this. You should know this. This is very important. So if you go back to that same energy level diagram which I showed you, this is 1 electron volt. What is this? This is 1 electron volt. So if I have written it down in your notes, please write 1 electron volt over here. This is much larger than 1 electron volt. It's very high. Okay, it's very high. This is 1 electron volt. Keep this in mind for a semiconductor. Okay, very good, very good. Now, let me tell you that before we go ahead, I hope you know that, in case you do not know, I'm telling you, I hope you know that you're also simultaneously preparing to enter into the Ekalavya batch, because this Ekalavya batch is your one-stop destination for clearing JEE Advanced. Last year, through this Ekalavya program, we had more than 500, I'm not kidding, more than 500 selections for IITs from JEE Advanced, just from Vedantu. It's a big number, I'm telling you. And this time, this number is going to be huge thanks to all of you who are preparing so hard. So guys, there are best teachers, lots of assignments, lots of test series, lots of doubt solving, everything. And what is the best part about it? I think many of you know it. Well, the answer is very simple, guys. This is free of cost. What more do you want? Yes. So just one, I think hardly a few thousand students were there. Not even more than 2,000. It was 1,000 something students, and more than half cleared JEE Advanced. So it's a big achievement if you think about it. Rama, I'm not ignoring you, Rama. All right. Okay. So the link for joining the batch is mentioned in the description box. You need to have 96 or 97 percentile above. But for some reason, if you have got a lower percentile, you still have multiple entry points. You can join on 19th March, even on 1st May, and even on 29th May, because the JEE Advanced exam is after a very long time. So don't worry about JEE Advanced right away. But yes, there are multiple entry points, even if you have scored little bit less for some reason. So last year, I also taught in Ekalavya batch. So I know how rigorous the preparation is. So I feel you should definitely take this like a motivation for joining or for scoring really well in the March attempt or even in the April attempt. All right, very good. Yes, very good, Sahitya. Prepare for the Ekalavya batch. So doctor is my life aim. The link is in the description box. And if you're a NEET student, there is going to be a separate Ekalavya batch for NEET also. I'm telling you now only, secret is out. Okay, so there is going to be a separate Ekalavya batch for NEET also coming up very soon once the NEET dates are going to be announced. Look at that, the doctors and the Princy Kapoors, very good, Asta and all are slowly giving all the love out there. Thank you, thank you. Okay, great. Chalo, let's get going to the next one. Come on, let's pay attention. So we are going to now see how to use semiconductors, what exactly is there in a semiconductor, and what are the different types of semiconductor. Yes, let's do this. Let's do this. Okay, now to tell you about it, yes, let's talk about, how a semiconductor is made. In a semiconductor, you have all those kind of atoms which have small band gap between the valence band and the conduction band. So in a semiconductor, what do you have, guys? A small band gap between the valence band and the conduction band. Now, when you have so many atoms like this, example silicon, germanium, these are standard examples of semiconductors. Okay. Now, there is a very interesting thing that happens once they form bonds, and that's what I want you to see. So they have formed bonds. These are all the semiconductor atoms forming a big chain-like structure. Now observe this. Observe this. When you have these semiconductors at room temperatures, they are not going to stay still. They are going to oscillate, they are going to vibrate, they are going to rotate, they are going to twist, they are going to move around because of the thermal energy. And when they often vibrate, you're going to see that many times the bonds will get twisted, they will be strained, and they will get broken. I hope that's clear. So when these atoms vibrate, twist, they produce strain, and these bonds get broken. And once a bond is broken, you will have an electron which is going to be free. Yeah, you're going to have free electrons. I hope that's clear. So you're going to have free electrons, and there is going to be a vacancy over here. These two atoms will be like, hey, this electron left us. Oh my God, who is going to fill the void? So there is a void created in their lives. They're going to be very sad about it. This electron has left them because of the strain in the relationships between them. I hope that's clear. So guys, that vacancy, what is it called? That vacancy is called as a hole. Alright. So electron hole is the lack of an electron at a position where one could exist in an atom or atomic lattice. So this is a void which is called as an electron hole, and this electron has left them. Now there will be so many holes and so many electrons spread across this lattice or this structure of crystal. So somewhere else, some other bond, some other two people are having a very difficult time. They are having a strain in their relationship. So again that bond gets broken. There is a vacancy out there. Again there is an electron. Now you will be wondering, what are these electrons going to do? What are these electrons going to do? What are these holes going to do? These electrons are free. Nobody to stop them. They are going to roam around. This electron will roam around somewhere. This electron will also roam around somewhere. And while they are roaming around, these holes can capture them because they are very eager to capture some electron. There is a void. There is a void in the relationship. They want some electron to come over there. So they will capture those electrons. So maybe some electron will go and fill up the void somewhere else. This electron will fill up the void somewhere else. Another electron will fill up the void somewhere else. So you will see, for example, if this electron has created a void here. Imagine this. If this electron, oops, my bad, one sec. If this electron has created a void or a hole over here, and this electron goes and fills up this void over here, then can I say the hole has shifted from here to here? Think about it. I'll repeat. If this electron fills the void here, the hole which was over here will be satisfied. So can you now see the hole which was here has now shifted over here? Can you see the hole has shifted? Can you see that the hole has shifted? Yes, very good. Similarly, if this electron fills up this void, then again this hole gets satisfied. Now at any given point of time, you will have equal number of electrons. Yes, Aishwarya, holes are positively charged. You can think as if they are positively charged because they lack electrons, correct? So think about it this way. You will always have few electrons going this way, few electrons going that way, few holes going this way, few holes going that way. So in net effect, the net effect will be zero. In total, if you add their effects, will be zero because equal electrons going this way, equal electrons going that way, equal holes going this way, equal holes going that way. So net, yes, the net will be zero. Keep this in mind. Okay, net will be zero. It's just like saying, all right, it's just like saying, see guys, holes are, if you have a sphere, if I take an electron out, then what will be the charge on the sphere? Will it be positive or will it be neutral? From a neutral sphere, if I take out an electron, what will be the charge on the sphere? Will it be positive or will it still be neutral? Understood? So that is basically a hole. Yes, so the sphere will become positively charged. So similarly, If an electron deserts an atom, then there will be a positive charge developed over here. Excellent, very good, excellent, excellent. Yeah, okay, clear. So look at this. This electron will wander around. These two electrons are wandering around, and they can again satisfy and fill up the gaps. They can fill up the voids, and again you will have bonds. Again, this process will keep on repeating itself. Now, I want you to understand what exactly will happen if you connect a battery across them. If you connect a battery across them, pay attention, guys. Pay attention. Just one, pay attention right now. All right. How does the void shift, Devki? Because the electron will fill up the gap. So if there is a void which is created here, if an electron jumps and fills up this void, so this void is gone. So that new void is created here. It's as if a void has shifted from one place to the other. Okay, great. Now my point is, the net current is zero. All right, the net current is zero. Now the moment I connect a battery, what do you think will happen? What do you think will happen? Yes, it will begin to conduct. There are electrons, there are holes. Look at this. The electrons will immediately start flowing over here, and you can see the holes flowing towards that side. Look at this. This is positive terminal. This is the positive terminal. Okay, and that's the negative terminal of the battery. What do you see? The electrons are coming from there and going like this. Do you see the hole getting shifted from left to right? Guys, can you see the hole getting shifted from left to right? Adesha, like I said, the bonds get broken because of the thermal collisions and the thermal energy. There is a lot of strain. Remember I just told? Yeah, because of that. Yes. So guys, in a case of a semiconductor, think about it. If there is some external battery, if there is some external electric field applied to a semiconductor, then the electrons and the holes both will conduct in the opposite directions. Look at that. Electrons are moving here, holes are moving there. So will their effect cancel out each other? Yes or no? Will their effects cancel out each other? Geeta is saying already the currents are moving in opposite direction. Come on, think about it and let me know. Let me know. Will the effect cancel out each other because electrons are going here, holes are going there? Will it cancel out each other? Nick says no. Aishwarya Princey say yes. Intrinsic means there is nothing else apart from that semiconductor atoms, just one. It's pure semiconductor, nothing else, no impurity in that. That's the meaning of intrinsic semiconductor. All right. So a lot of you are saying yes, some of you are saying also no. Let me tell you, they will in fact not cancel, they will in fact add. I'll tell you why. See guys, understand one thing clearly. It's the negative charge which is going this way, and the holes which are positive charge going that way. Negative charge going this way is same as another positive charge going that way. Isn't that correct? That's what you have learned in current electricity. Electrons going this way is same as current or positive charge going that way. Correct guys? So there is already a positive charge which is hole which is moving, and there is already an electron which is moving. So understand, both of them, their effects will actually add, and that's why the current in the circuit is in this direction. Is that clear? Is that clear? I hope this is clear. Yes, a lot of people make mistake in this. So the conduction, this kind of question has come in JEE Mains. The conduction in a semiconductor is because of hole current as well as electron current. Keep this in mind. Yes, both the things are going to matter. Excellent. Very, very important. Now, this is also an important line. When you increase the temperature, the number of electrons, the number of holes will also increase. All right, because more collisions, more strain of the bonds, more bonds will get broken, more electrons will be free, more holes, more conduction, and hence the resistance will decrease. Very important line. All right, very good, very good. Okay, Satish Chandra Verma, this is not a Hindi channel. There is a separate Hindi channel. This is a pure English channel for all the English medium students. All right, I hope you understand that. All right, cool, excellent. Thank you, Anshdeep Rehal. Very good, Dora Buji. Magnitude of current will be more, or will it remain the same? So Anshuman, because both the currents will add up, so that's why the current will incorporate both the whole current as well as the electron current. So it will be slightly more, you can think of it. If only electrons were contributing, then it would be less. But even hole current contributes. So that's why considering both their effects, it will be more. Very good. Excellent. Excellent. Thank you, Rohan Kumar. All right, let's get going. Okay, very good. All the new people joining here, we are discussing semiconductors, we are discussing logic gates, transistors, as well as their applications with problems and PYQs. We are somewhere midway. In case you have joined in late, it's okay. You can replay and catch up at 2x speed. And I hope you have already hit the subscribe button so that next time you do not miss the lecture. And if you are already here and subscribed, do not forget to smash that like button out there. Now, let's talk about mobility and conductivity. Very important formulas coming up for all of you. Very, very important formulas coming up for all of you. I hope you are going to write it down. Very, 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 very important formulas, guys. Okay, so what are these important formulas? Now, the first thing that you should know is that, remember in current electricity, I had told you electric field is rho into J. Electric field inside a conductor is resistivity into current density. Now, let's rephrase this particular equation and see what exactly happens. Thank you, Bhavani. Come on. I'm going to write it as 1 by rho. All right. Rho comes below. It will become J by E. Now, 1 by rho is called as conductivity. So, if this rho is resistivity, okay, then this sigma is called as conductivity. Oops. Okay, so this is called as conductivity. Okay, now this J is current divided by area, right? Current per unit area into electric field. Now next step will be sigma is equal to, remember I have given you a formula for current and drift speed and number of electrons per unit volume. I is equal to NVIDIA. I is equal to NVIDIA. So yes, Rohit has almost guessed it. Very good. So it will become N VD E A and this A and this E over here. Now I can clearly see what is going to happen. This area and this area will cancel out, and therefore I will have sigma is equal to, now comes the tricky part. Here what I'm going to do, I'm going to take this and this in bracket, drift by electric field as one single term, and I will define it as mobility. So E is there into mu. Now this mu is called as mobility. So mobility of atoms is nothing but drift speed divided by electric field. Keep this in mind. So this is very important formula, Ne mu. Mu is mobility. Keep this in mind. Okay, very good. Thank you, Sanjay, for all the love. Okay, excellent, Kanu, excellent. So very good, very good. Now, after this, Satya, don't worry, beta. Just concentrate on the session. There will always be haters, and I will never bother about haters because your love is more than the hate that I receive. Obviously, I'm on YouTube. I'm bound to receive some hate. That's a part and parcel of my life. But it's your duty to spread the love. You are going to be our minions. You are going to be our mascots. You are going to be our promoters. You are going to be our supporters who are going to make this channel grow because of your love. Because it's a two-way relationship. You love us, we love you. That's how it is. And we are going to make sure that the hate is negligible as compared to the love that we receive. Yes, correcto. Now, let me tell you one very interesting thing over here. I just told you that in a semiconductor, the conduction is because of hole plus the electrons. So now comes the real magic over here. There are questions from this in JEE Mains. Guys, the sigma in a semiconductor, alright, it is sigma because of the holes plus the conduction because of the electrons. Very, very important. Remember, they are not going to cancel, they are going to add. So that's why it will be sigma's formula, Ne mu, right? So N of holes into charge is E only, into mobility of the holes plus number of electrons per unit volume of electrons into E into mu E. So this is the sigma of a semiconductor. Very, very important formula. You should know this. all the values will be given to you. Don't worry, it will be given. But people don't know this formula. That's why they don't do this problem. Yes, very good, very good. Excellent. Excellent, excellent. Yes. So Chakraborty, I think the results should be out within another 2-3 days. Okay, I hope you have noted it down. Very good. Thank you, Diya. Thank you, thank you. Princey, thank you. Everyone out there for all the love. Yukta, thank you. Tensai, thank you everyone. Thank you, Satyapriya. All right, cool. Now, very good. Minyanarthi has noted. Excellent. Asta is copying. Very good. Take a screenshot. Very, very important. Hey, kya baat hai, Suman Kumar? This reminds me of the regular school days. Roll number 30. Blue house copying. Very good. Yes. Enrollment number 2101. Very good. Very good. Done. 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 Let's get going to the next concept. Ooh, we were talking about intrinsic semiconductor. Now, intrinsic semiconductor is nothing but where there is no impurity. It's pure atoms of that silicon or germanium or whatever. That is intrinsic. There is no impurity. But when you add impurity, now you'll be like, so why the hell would you add impurity? Guys, that's a whole part of semiconductors. Remember, for semiconductors, very, very important that the conductivity depends on what is there in that lattice. That lattice which is there, alright, that impurity is going to make a huge difference in the conductivity. And that's what doping or impurity does. If it's pure, it has some level of conductivity. You can greatly change the conductivity by adding some impurity, by adding some extra electrons or creating some extra holes. And that's what it's going to be. So an extrinsic semiconductor can be made by adding impurities. Now there are two kinds of impurities that you can add. Yes, correct Devki, depends on what it is doped. Now there are two kinds of doping. One is you provide excess electrons. Second, you create extra holes. Oops, one sec. You create extra holes or you create extra electrons. Both ways you can increase the conductivity. You will be wondering how. I'll show it to you via energy level diagrams and you will beautifully understand it. It's not that difficult, I'll tell you. See, one thing is very clear. Adding these electrons makes it available for conduction because, see, the other electrons are just involved in making bonds. So these extra electrons can greatly influence the conductivity. Similarly, creating extra holes can also increase the conductivity because these holes will be on the constant lookout for newer electrons. So they will quickly grab electrons. So those holes are eager, they're desperate to fill those voids out there. So let's talk about N type of extrinsic semiconductor. N type. Now N stands for negative. What is N? Negative. Negative means more electrons. Excellent. Yeah, Devki, they are free electrons. Excellent. Now look at this simulation, very simple. This is silicon lattice. You have placed a phosphorus atom somewhere in between. There are a lot of phosphorus atoms out there somewhere in between. Now this phosphorus atom, it's a pentavalent impurity. That means there is one extra electron available. The 4 electrons in its outermost shell will form bonds with the other 4 silicon atoms. But the extra electron, it will like what to do? It will roam around. It's like a free electron and that increases the conductivity. So if you look at it via energy level, do you remember there was a small gap between the valence band. Remember the energy diagram for a semiconductor. There was a small gap for valence band and conduction band, correct? There is a small gap. What if this atom makes another sub band over here of electrons? So instead of the electrons jumping from here to here, now they only have to jump from here to here because of the phosphorus atoms, the impurity which is present. So can you see the energy required to overcome this jump is much lesser because of an extra band which is present over here. So isn't that increasing the conductivity? I hope that's clear. Yes. No, Charan, pentavalent is not for extrinsic. Intrinsic, no, that is wrong, Charan. Intrinsic means pure. There is nothing in it. Extrinsic has two types, N type and P type. Okay, Charan? I hope that's clear. Hello, Sujal, welcome. I guess you joined a little bit late, but I hope you can replay it back. Okay, clear, very good. Now, similarly, P-type extrinsic semiconductor. So, I hope you noted down those examples also. Antimony, phosphorus, these are examples of the pentavalent impurity. Ashish, please don't spam. Okay, Sujal, I think you should join the Telegram group, alright, so that you get all the important notifications. And very important thing, you can also hit the bell icon out there, bell icon, and say that you want all the notifications. That's how it is. Now, the next thing after N type is P type. Imagine instead of all the silicon atoms there, you replace one of the or few of the silicon atoms with an atom like boron, alright, which has fewer number of electrons. Because it has fewer number of electrons, there will be one bond which is less. If there is one bond which is less, what will it create? It will create a hole. And what does a hole want? It wants an electron. It wants the hole to be filled. It's very eagerly looking for an electron. So this is again going to create an extra hole, thereby increasing the whole conduction current, and because of which the effective current will increase. So extra hole current, extra conduction, that's why the net conduction increases. And if you look at the energy level diagram, remember there was a small gap between valence band and conduction band, 1 electron volt. So creating this extra hole creates another layer, alright, another layer, very important, another layer of vacancy which can be easily filled. It creates another layer of vacancy, another sub-band between the conduction band and the valence band where the electrons can easily jump. That is what you should understand. Is that clear? So an extra layer, an extra band is created both for P-type as well as N-type, which helps in the conduction. Correct. The band gap reduces effectively. So Deepali, which part you did not understand, please let me know, or you can just replay back the same thing again and again. All right. So very important. Very good. Ohm Dok, superconductor is nothing but something which can conduct very easily, almost zero resistance, and that will only happen at 0 Kelvin. All right. Okay, cool. So great. Okay. So basically what you should understand is that, Sujal, that when you give temperature, then the electrons from the valence band can easily jump into the conduction band because of the collisions, and they get knocked out and they go into the higher energy levels. That's all you need to know. Okay, so don't worry about the Fermi levels and all that. Okay, very good, Satyapriya, excellent. Okay, so again, let me be very clear about this. See guys, for normal semiconductors, there is no impurity. Okay, there is some energy gap between valence band and conduction band. When electrons or atoms collide, these electrons jump from the valence band into the conduction band. And because of that jumping, there is some decent amount of conduction. But when you add N type of impurity like phosphorus, that extra electron is also available for conduction. And when you add a trivalent impurity like boron, it creates a hole which is also available for conduction. And the energy diagram shifts like this. So basically understand, when you add N type of semiconductor, alright, there is an extra energy layer which is created, which makes that jump really easy. I hope that is clear. Yes, it creates an extra energy layer which makes that effective band gap lesser. That's what you need to understand. Okay, so both, even for P-type and even for N-type. Very good. Okay, so with this, let's get going to the Questions out there? Come on guys, start answering the questions. If Np and Ne be the number of holes and conduction electrons in an intrinsic semiconductor, then which of the following is true? Come on, Tejas says B. Come on. For an intrinsic, B for Bombay. Sure. All right. Very good. Excellent. Very good, guys. The correct answer is B. Acha. If it was extrinsic semiconductor, guys, if this word intrinsic was not there, then if instead of intrinsic, if it was extrinsic, then which one will be the correct answer? Then which one will be the correct answer? Be careful. Then which one will be the correct answer? Come on, come on, come on. No, Devesh, Zener Diode will start in a bit. Then, yes, some of you answered it correct. Yeah, it could be either A or C. That means it will be option D. It depends whether it is P type or whether it is N type. It could be anything. It could be anything. Yeah, Preksha, correct. You should tell me whether it is N type or P type. So if it is N type, there will be more electrons. If there is P type, then there will be more holes. Correct. I hope that is clear. Yes, you should tell the type. So if it is not mentioned, you will mark D. You do not know. Information is not given. You can only conclude this. Can you conclude this? Can you conclude this? No. These are question marks because the type is not mentioned. But if the type is mentioned, then I can tell you which one is correct. Okay, very good. P or N type. Excellent. You guys are slowly understanding it. 2017 question, I'm not even kidding. Look at this question. The conductivity of a semiconductor sample having electron concentration of this, hole concentration of this, electron mobility, I just told you mu of this, and hole mobility of this has a total conductivity of which of the following? Solve it. I'll give you 1 minute. Let's see. I'll put a timer. Come on, minions. I want you to do this. I'm going to put a countdown timer out here. Let's see how many of you do this. Yes, Gopala. A or C will depend on the type. Excellent. Very good. Very good. Clear. Oh. क्या बात है सत्यप्रिया जय हनुमान. Okay. Come on, come on, come on, come on. 1 minute timer. Shreyas Sir's minion already says A. Okay, let's see. Direct formula based. Not that difficult. You should be able to get it. Velaga says A. Abhishek says A. Okay, interesting. Dinesh says C. Basanti has got a lot of people, I hope. Okay, says B. Okay, a lot of you are saying A. Just one saying 1.69, 67, sorry. Achyut says A. Okay. Omdog says C. Devesh is confused between A and C. Tan, tan, tadan. The answer is A. And I'll tell you why it is A. Because you have to just use the formula. And what is our formula, guys? It's very simple. So, sigma is nothing but, I just told you, sigma is nothing but NH E mu H plus NE E mu E. Everything is given, believe me. NH, whole concentration. Whole concentration is 5 into 10 to the power 19. E I will substitute in the end. Whole mobility is 0.01 plus electron concentration 5 into, so this is first term, and second term is 5 into 10 to the power 18 into E into electron mobility, which is 2. Now solve this, guys, you will get the answer. It's very simple. Yes, and you're going to get it as 1.68. Okay, very good. And this value of E is nothing but 1.6 into 10 to the power minus 19. So many things will cancel out. Correct. Guys, believe me, if this question comes, I'm pretty sure if somebody has not attended my class today, they will leave this question. I mean, think about you. If you didn't know the theory of semiconductors before this, then that's it. You will feel that this question is difficult. But now you feel that this is easy because you have just learned the formula. So guys, please revise these formulas and make sure you know them, and do not leave these questions because they are very easy questions, direct formula questions, nothing great in these questions. Very good, VK, excellent. Let's get going to the next one. Coming to PN junction. Easy peasy lemon squeezy. Cool. Yes, Devash, hold on beta. I'm going to come to Zener Diode also. Don't worry. Transformers is a part of AC circuits. I have taught it over there. Now coming to PN junction. Now what is a PN junction? You take a P type of material and you take a N type of material and bring them close together. P type and N type. P type has lot of holes. N type has lot of electrons. P type has lot of holes. N type has lot of electrons. Does that actually mean that N type has no holes? Nah, N type has holes. Does that mean P type has no electrons? Nah, it has electrons, but they are very few in number. They are minority. Majority in P is holes, minority is electrons. P positive, more holes. N negative, more electrons, less number of holes. Is that clear? Yes, they are already doped. P is doped by P type material, N is doped by N type material. Excellent. Excellent. Thank you, Satyapriya. Yes, thank you, Preksha. Very good, Lekha. Clear? Excellent. Now, think about what they would want to do. Feeling, try to get a feeling. This N type has excess electrons. They are desperate, they are going around everywhere. A lot of phosphorus. Here, boron, lot of holes, very eager. They want to capture electrons. What will happen, guys? Think what will happen. This guy wants something, this guy has that something. P type wants something, N type has that something which this guy wants. Wants something, it has something, obviously demand meets supply. Clearly, transfer, very good, Priyal. Yeah, electrons will enter. Very good. Now this process of these electrons going from this N type to P type, this process is called as diffusion. What is it called? Diffusion. Yes, marriage is going to happen. Zap karke these electrons will be, hey, we found holes, come on, let's go, yay, hooray. It's like there is a birthday cake and you all minions are over here. Lot of birthday cakes are here and you want that birthday cakes. All of them are going to jump. But you know, within no time there is going to be crowding. There is going to be crowding. Oh, by the way, I forgot to tell you one thing, and this is a common mistake. Okay, just imagine the marriage has not yet happened. This is still as it is. This is still as it is. Is N type positively charged or negatively charged? Come on, guys, answer this. Is N type positively charged, negatively charged, or neutral before the marriage, before the transfer? Before the transfer. Good one, Sujal. Okay, positive, negative, neutral. Okay, very few people got it correct. I think Priyal got it correct. And well, no. I'll tell you what, it is neutral. Yes, you might be wondering, what the hell? I thought it had excess electrons. Sir, you must be really kidding. Let me tell you guys, I'm not at all kidding. If I go back a little bit, and when I showed you this N-type material, all right, it had excess electron, right? It had excess electron. You might be thinking this N-type is negative, right? No, it is not negative. It is not negative, achha log. Even the nucleus has one extra positive charge, na? It is not having, think this proton, there is one extra proton here. It's not silicon anymore. Understood? Understood? Yes, positive the nucleus. Correct. Correct. Understood, guys? So, I'll repeat again. N-type is not negatively charged. It just has an electron available freely. Understand the difference. An N-type is neutral, just that electron is available freely. Understood? This is a common misconception. Correct. There is a positive on the nucleus. Correct. Extra positive on the nucleus. This is phosphorus, not silicon. Similarly, is P type, positively charged or negatively charged or neutral? Come on guys, answer this very quickly. Quickly. Is P type positive or negative? Come on, answer quickly. Is it positive, neutral? Yeah, very good. It's neutral. Like, sir, there is one electron less, so it should be positive. Nah, beta, there is one proton less in the nucleus. Understood? So there is one proton less in the nucleus, so it will nullify. Very good, excellent. It will nullify it. So that's why they are neutral as such. So this is neutral, this is neutral. Now, when the boys' hostel sees the girls' hostel, when the minions see the cake, when the electrons see the holes, when these electrons go to the holes, what will happen? The neutrality will go away. The neutrality will go away. Do you agree with this? Do you agree with this? Everybody agrees with this. So when the electrons go from here to here, what will the n-type become? What will the n-type become? Positive, correct. And what will the p-type become? Think about it. What will the p-type become? It will become negative. Isn't that clear? Excellent. So n will become positive, p will become negative. That's what is interesting. Correcto. And this is what this simulation shows. Excellent. Look at this. This is the n region. This is the p region. Did they move? Oh yeah, I think so. They moved. Okay. This simulation is going to replay. Okay, this simulation is going to replay. Forget what is the depletion zone. I'll come to it in a bit. Look at that. The electrons went. These filled up. They filled up the holes. It becomes positively charged. This becomes negatively charged. P becomes negative. N becomes positive. Is that clear? Is that clear, everyone? Yeah. Look at that. These boys from the boys' hostel have gone to the girls' hostel. They have gone into a relationship. This has become positively charged. This has become negatively charged. Very good. Excellent. So Preksha, when we say that n-type has more electrons, that means more electrons available for conduction, not in total. So there are equal number of protons also, but they are in the nucleus. The protons are not available for conduction, Preksha. I hope that is clear. Yeah. Very good. Excellent. Now, once you get positive and negative charge, now there comes a problem. They will form a barrier. Warden has come, guys. Warden. Who is this? Hostel warden. Oops. Where is it? Yeah. So the boys went to the girls' hostel out there, and there you go. You are going to get a potential barrier, and that is what is important. Yes. Okay. This is called as the depletion layer. This is the warden, hostel warden. It's going to be like, hey, thamba, bas zhala, ho gaya, that's it, ruko, stop. Why? Because, think about it, this is negative charge. And who is trying to go? Negative charge. So it will be like, no more further electrons can go through this barrier. So this is the depletion region, and you will see that these electrons will be stopped because of these electrons out here, the negative charge, and the holes will be prevented to go from that here to that side because of this positive charge out here. Is that clear? Okay, I hope this is clear. So Nirmal, I have explained why holes are positively charged, etc. At the start of the lecture. I would request all of you who have joined in late to watch the replay of the session. All right, very good. Now this is called as a depletion layer because that's it. After this, the process will stop. And also, there is one interesting thing that happens. If you look at the concentration of holes and electrons, once the diffusion happens, you will see the electrons from the n-type are plenty in number on the n side, but they slowly reduce, and in the p-type there is hardly any electrons. In the p side there are more holes, and the number of holes keeps on reducing, and obviously in the n side there are very few number of holes out there. This is called as the depletion zone. In the depletion zone, like I just said, the p-type is negatively charged, the n-type is positively charged. Do you see this electric field? Do you see this electric field from positive to negative? It's like a capacitor. It's like two plates. One is positive, one is negative. Electric field coming from that side to this side. Now, If this much is clear, understand one more thing, guys. Understand one more thing. If there is an electron or a hole which is created, in this region, this is no man's land. If there is an electron or hole created, why will it be created? Because of thermal collision, because of twisting, because of strain in the relationships even in this region. There are a lot of holes and electrons here also, correct? So guys, understand what will happen is that the moment there is electric field, what will happen? This positive charge will move here, correct? Force on the positive charge will go here and this electron will try to move here. Now think about it. What is the net direction of current? What is the net direction of current because of this? Positive charge goes here, electron goes there. Electron going there is same as another positive charge going this side. So there will be current going this way. Do you see that? There will be current going this way. Everybody understands this? Everybody is understanding this? Yes, very good. So electron going towards the right is same as positive charge going left side. So you will see a current which will be going this way. And how did these negative charges come? Because electrons came from here and the holes came from here. So because of this, think about it, electrons going here is same as positive charges going that way. The current is this way. This current is called as diffusion current. This is called as diffusion current, which starts initially. The electrons from here go here, the holes from here go there. So the current goes that side. This is called diffusion current. But the holes and the electrons here, all right, they create a current this way. This is called as the drift current. Is that now clear, everyone? Yes. So there is a drift current and a diffusion current. Everybody understanding this? Everybody understanding this? Yeah, very, very important. Very, very important. So inside this zone, whatever gets formed will cause drift current. Outside this zone, whatever transfer happens, that causes diffusion current. Excellent. So when nothing is connected, this current and this current, what will it be? What will happen? When nothing is connected, what will happen? This drift current and diffusion current, what will it be? Will it be more? Which one will be more? Or will they be equal? Glad you guys are enjoying. Yes, net current will be zero because they will cancel out each other. There will be a dynamic equilibrium. Constantly electrons going from here to here, electrons coming from here to here, electrons going from here to here, coming from here to here, holes going from here to here, coming from here to here. So constantly they will be circulating, net current will be zero and they will cancel, something like a dynamic equilibrium. Yes, I hope this is clear. Monkey, let's concentrate, monkey. Okay, chalo, very good, excellent. So that's the next slide. Drift current, hole current, everything, diffusion current, everything is mentioned over here. Very important slide. Write it down, try to understand this. Diffusion, electrons go from here to here, holes go from here to here. So diffusion current is like this. I diffuse. Okay, I diffusion is here. This is drift current, I drift current. And generally they are equal at no biasing. No bias means the voltage difference is zero. You have not connected anything. If you do not connect anything, there is equality in both of them. Both of them are equal. Excellent. Okay. Yes, let's get going to the next one. Okay, I hope you have written it down. Meanwhile, I'll just grab some water. Thank you. Very good, very good, very good. Devesh, hold on, bacha. We are coming to diode. Amazing. So, going to the next one, erasing this now. Okay, going to the next one. All right. Okay, so drift current happens in the depletion layer, because of which the electrons Anshuman or the holes go back, they are replenished back into the p type or the n type. Okay, Anshuman? Yes, drift current happens in the depletion layer and they will come back, the electrons, the holes get replenished at the border. Yes. Now we'll talk about forward biasing. Okay, now forward biasing means connecting P to positive, N to negative, as simple as that. P to positive, N to negative. Look at this, P is positive, P is connected to positive, N is connected to negative. What will a battery do? It will supply electrons. Look at that, electrons are coming from here. And where are they entering? They are entering inside the N region. Now you might be wondering, sir, N type already has so many electrons. Why are you giving it more electrons? Nothing like that. See, this side is already connected to positive, correct? Now when you connect it to positive side, what will happen? The electrons which are already here, they will get sucked. Now these electrons will in turn pull the electrons here. They will pull the electrons in turn here. So you will see the circuit gets completed, because electrons will jump from N to P and P to, they will go across the battery and come back over here. So the circuit gets complete, but there is one small problem. They have to overcome this warden. Yes, they have to overcome this warden, this depletion zone which is created, that barrier which is created. I hope this is clear. So what happens is, when you connect a battery, you first need to destroy this barrier. So when you connect a battery, this barrier becomes smaller until there comes a point where it vanishes. So there comes a point when this barrier becomes smaller and smaller and it vanishes. After that, the electrons can easily flow. That wall is destroyed. It's like, the electrons have to climb up this wall and go. So if you connect a strong voltage, that wall gets destroyed and the electrons can flow very easily. Yes, that depletion layer goes. Yes, very important. Now, guys, concentrate. Do not focus on Ramesh Pokhriyal or other things now. You are coming here for learning. Yes, very important. Now, when you plot the graph of current versus the voltage in forward bias, P to positive, N to negative, very important. There is a particular voltage only after which the conduction happens. That voltage is called as the knee voltage. So generally it's around 0.3 volts for germanium and 0.7 volts for silicon semiconductors. So this is something which you should remember. Okay, I'll come to that in a bit, but don't worry. There is a voltage which you need to apply only after which the conduction suddenly shoots up. Look at this. That voltage after which the current shoots up, that voltage is called as the knee voltage, and that is 0.3 for germanium, 0.3 for germanium and 0.7 for silicon. Keep this in mind. Is that clear? Yes, very important. And this is called forward bias, and this is how current changes with voltage. For most of the voltages, hardly any current flows. Suddenly the current shoots up, alright, for higher voltages. Yes, Richu, we are going to talk about transistor as well. Now, next thing. So, like I said, Bhavani, it's called as a knee voltage, all right, that will be given to you. Okay, next thing, reverse bias. You connect negative to positive, positive to negative, as in P type to negative, N type to positive. Now that's the worst thing you can do. All the electrons will try to move here because you are connecting it to positive. All the holes will get pulled by this negative. So this depletion zone, this no man's land, this warden will become stronger, this wall will become bigger, and you will not see conduction happening. That is very bad to, dangerous case. Excellent, very good, guys. So That is something which is very important. So when you connect n-type to positive, p-type to negative, that will create a big wide depletion zone. There will be no current which will be flowing, and you will see that you can keep increasing the voltage. Look at that, you can keep increasing the voltage. There is hardly any current. The current is downwards, it's in the negative direction because you have flipped the terminals of the battery. So what you are going to see is hardly any current for even large voltages until it finally gives up. The depletion layer keeps on becoming bigger, and it gives up, and that's when the breakdown happens. Yes, so in reverse bias, is a diode conducting? Yes or no? Come on minions, answer this. Come on minions, answer this. In the reverse bias, is a PN junction conducting or non-conducting in reverse bias? Think about it. Think about it. Yes. No, it is not conducting, except very good, excellent. Unless it reaches the breakdown, it is non-conducting, and that makes the complete characteristic. So if this is n-type, this is p-type. All right, depending on how you bias it, how you connect the terminals, it will behave like a switch or a valve to allow the current or to not allow the current. In forward bias, for small voltages only it starts conducting. So this is forward bias. Typically very small voltages, 0.3 to 0.7 volts, the current increases rapidly. But in the reverse bias, it does not allow current until you reach the breakdown voltage, which is huge. Very important. No Sujal, you will not be asked anything else apart from germanium and silicon, don't worry. Yes, now that's why a PN junction is called as a diode. Now what is a diode? Even your heart has walls. Blood can only flow in one direction. Do you know that? All right, there are walls inside, even in your body. The blood can only flow in one direction. So that is very important. So understand that a PN junction also is like a wall because it only allows current in forward bias and does not allow current in the other direction. Very good. I hope this is clear. So the symbol for a diode is this one. Very important. N-type is this. P-type is the wider base of the triangle. Keep this in mind. Yes, this is P side, the wider base of the triangle. The pointed edge is always the N-type. Keep this in mind. Very good. Okay, let's get moving ahead. Next question on your screen. If the two ends of, come on. If the two ends of PN junction are joined by a wire, then what will happen? Come on minions, quickly. What do you think is the correct answer? What do you think? Bani says C. Okay, D, B, A, C, D. Okay, if two ends of a junction are joined, if you join it using a wire, think about it. Nothing should happen, guys. Remember, they are electrically neutral. They will diffuse, drift, equilibrium is achieved. That's it. You're not connecting a battery, you're just connecting a wire. Nothing will happen. There will be no current in it. That's it. All the currents will cancel out each other. Think about it. I hope it is clear. Some of you got it as a very good Aishwarya, very good Achyut. All right, very good Pooja. Okay, understood Abhishek? Yes, very good. So understand, if you take P and N, it's a wafer. There is diffusion, there is drift, which is happening. If you connect it, what will happen? Nothing. There is no current unless you apply a potential difference, unless you bias it. Okay, if you do not believe me, go back to the diagram. What is this point? Zero voltage, right? What is zero voltage? Nothing is applied. What is the current? Zero. Do you see this graph passes through zero? So no voltage, no current. Keep this in mind. Yes. Astha, no, logic gates will start in some time now. Next, diffusion current in PN junction is greater than the drift current in magnitude. Then, is it forward, reversed or unbiased? Or it will never happen. Come on guys. Yes. Come on. Think. Priyal says A, Abhishek says B, Sujal says D. Come on minions, don't let the Joes die down. Okay, I'll tell you what. See guys, who is more? Diffusion is more than the drift. So then the junction will be in forward bias. Yes, it will be in forward bias. Recollect the diagram. Diffusion happens from, for electrons it goes from here to here. For holes it happens from here to here. So the actual current, the diffusion current is this side, right? And when you connect it in forward bias, this is positive terminal. That means the current will come like this. The net current will be like this. That means the diffusion current must be more than the drift current. Think about it. So diffusion is happening there, drift is happening here. Total current is flowing like this from P to N. This is connected to the positive side of the battery. I hope that is clear. Very good Anu, very good. Yukta, Asta, very good. Soham, excellent. Yes. Now going to the next question coming up on your screen. So Sujal, that's what I'm saying. Remember this diagram. I just gave it some time back. Hole diffusion, how does it happen? Holes go from P to N, right? So diffusion is also happening this side. Drift will happen this side. Forward bias is this way. Reverse bias is this way. So if you remember that, that's it. Next question. Very good Bhuna, very good Minyanarthi, very good Dora Buji. All right. Any specific time? No, Achut, it's not on time, it's on voltage. Okay, come on. Bani Krishna, I am guessing you joined in late. My dear student, you need to replay the parts which you have missed, Bani, so that you will understand everything, because I think you have missed diffusion and drift. Okay, come on. Think about this. How do you solve this? This was a 2018 question. Rohit, isn't this a PYQ? And many questions which I gave even before this, Rohit, were PYQs. Maybe I did not mention the year, but they were actually PYQs. Okay, Rohit? Concentrate, come on, guys. Okay, so, well, I'll tell you what, it's simple. First of all, it's a silicon diode. For silicon diode, what is the voltage drop? The voltage drop is, come on, how much is it? It's 0.7 volt. So 0.7 volt of drop is there. That voltage which drops in forward bias. Very good. So basically out of 3 volts, 0.7 is dropped here. So how much is dropped here? Out of 3, 0.7 gets dropped here, remaining will get dropped here. So how much will be dropped? 3 minus 0.7, which is nothing but 2.3 volts. So there is 2.3 volts across this resistance. So what is the current through the 200 ohm resistance? The voltage divided by resistance. What is the voltage? 2.3. What is the resistance? 200 ohms. So what will this give you? Come on, think about it. Come on, what is the answer now? Yes, finally. Tell me the answer. Come on, minions. Very good. 11.5. 11.5 into 10 to the power minus 3 amperes, which is 11.5 milliamperes. Excellent. Understood? That's how you solve these problems. They are not very difficult. These kind of questions have come in JEE. Okay, next question. Before that, let me tell you some applications of diodes. Thank you, Gaurav Hange from Pune. Love from Pune. Thank you so much from my hometown out there. Yes. 1.1 zarurat nahi hai, yes, don't worry about it. Just 0.3 and 0.7. That's all. Great. Now, diodes can be used as rectifier. Now, what is the meaning of rectifier? Rectifier means a device which converts AC to DC. A device which converts AC to DC is called as a rectifier. Now, remember, what does a diode do? A diode is nothing but like a valve which allows current only in one direction, and that too only in forward bias. Now, imagine guys, this is an AC source. Okay, imagine this is an AC source. Just imagine this is positive, this is negative. because there is a positive half cycle and there is a negative half cycle. So sometimes this is positive, this is negative. Sometimes this is negative, this is positive. If this is positive, this is negative, current will flow like this. It will go like this. It will enter here. Now, if you arrange the diodes like this in this particular manner, what will happen? Look at that. Once the current enters here, it has two ways, to go here or to go here. But what will this diode say? Hey, you cannot enter here. You will be reverse biasing me. But if the current goes like this, then it will be like, I can go. This is forward bias. So the current will go like this, correct? It will not enter here. And once it reaches here, again, it can't go like this because this will be reverse biasing it. So the current will go like that. It will go like this. It will go like this. It has jumped from here. Okay. It will go like this. It will reach here. Now remember, current can't go here because already there is current flowing here. So the only way it can go is like this, comes here, comes like this, and goes back to the negative terminal. Is that point clear? Is that point clear? No problem, Anshdeep, but watch the remaining part. Excellent. Excellent. Now, thank you, Drishti. Thank you, Jaswant, for all the love from TN, Delhi, and all the parts of India. Thank you. Thank you so much. Now, during the negative half cycle, this becomes negative, this becomes positive. Negative, positive. So the current will go like this, like this, like this. Now it has two options, go here or go there. Obviously it can't go here. This is reverse bias, so it will go like this, again like this, again like this, again like this, and again like this, again like this, and again over here. It won't be able to go here because already there was current coming from here. So it will go from this path, this path, this path, and come back to the negative terminal. What I mean to tell you is that in both the cycles, positive and negative, the current through this resistor always is the same. Did you see that? Did you see that? So if my current on the AC side, if my AC current was like this and like this, all right, this was, let's say, input, all right, my output, how is my output going to be? My output is always going to be in the same direction. It is always going to be in the same direction. So what is happening is that the current always flows in one direction irrespective of the current changing the directions here. So you have converted AC to DC. So that is one application of diodes. Is that clear? I hope this is clear. Is that understood? This is basically a simple application of diode as a rectifier. That's all you need to know. Very good. Yes, it basically flows in one direction. Amazing. Very good. Another application. So you should know all these things from NCERT. That's all. Zener Diode. Now this is very important. Now pay attention. Exam mein you will get questions from this. Okay. Thank you, Saiti, so much. Thank you for all the love. Now very important. Zener Diode is always used in breakdown region, all right, and in reverse bias. Very, very important. Now why reverse bias? I'll tell you. Look at this. I just showed you the IV characteristics of a diode. Voltage, current, forward bias, reverse bias. When you increase the reverse bias voltage, no current, hardly anything conducts. But there comes a Zener voltage. There comes a reverse voltage after which breakdown occurs. And look at this breakdown. It's like this, almost flat. Very important thing to notice, this is a constant voltage. Look at this voltage. This is basically a constant voltage no matter what the current is. The voltage in reverse bias does not change after a point across a Zener diode. Very important. Did you understand this? I'll repeat. The voltage in the reverse bias across a Zener diode does not change after a point. Now this is the fact we will use. because it has reached the breakdown voltage. Now you don't have to get into why this breakdown occurs and all that. That is irrelevant. You will learn this in detail when you take electronics engineering. Don't worry about why this happens, etc. No. Okay, concentrate on that. It happens. Just take it for granted. All right. Now, what I want you to understand is, imagine if I take a resistor like this, if I take 2 points like this, and 2 points here like this. I call this point as input and this side as output. Example, the breakdown voltage Vz for this Zener diode is 5 volts. Example. Thank you, Jai Bharat. And don't worry, the class is not completed. Yes, so correct. And what is important is that we are also going to do logic gates and transistors. Hold on. I hope you are not tired, because I am not tired. I am going to complete this topic. Okay? Cool. Is that, imagine my input voltage. See, this is in reverse bias. Do you see that? If this is positive, if this is negative, do you see that this is in reverse bias first of all? It's not in forward bias. I hope you see that this is right now in reverse bias. Very, very important. Cool? Clearly. Very good. Very good. Now, if this is 1 volt, all right, if the input voltage is 1 volt, then very less current will flow. The output will also be very small. The output voltage will also be there. Very small voltage. Small voltage will be there. If you increase the voltage to 2 volts, then this voltage will increase slightly. But if you make this 6 volts, then understand, out of 6 volts, 5 volts have to drop here, because that's the maximum voltage that can drop in a Zener diode. That's the maximum voltage that can drop in a Zener diode. So on the output side, you will have 5 volts and 1 volt will drop here. 1 volt will drop here. Similarly, if you make this voltage as 7 volts, then this will still be 5 volts, because the voltage drop should always be constant, and this will become 2 volts. If you make this 10 volts, then this will become 5 volts. If you make this 11 volts, this will become 6 volts. But this will always remain 5 volts. What have you achieved? What have you achieved, guys? Can you tell me briefly in the chat box? Can you tell me briefly what have you achieved using this? Understood, guys? What have you achieved using this? What did you achieve? No matter what the input is. Why, Soham? Because Zener diode beyond this voltage, what is that voltage? 5 volts. It will go into avalanche breakdown. That's it, gone. It has broken down. It will never increase the voltage. So after 5 volts, it cannot change the voltage. Yes, you are regulating the voltage. Correct, Tejas, Anirudh, Sayan. Excellent. It behaves like a voltage regulator in the breakdown region. That's what you need to know. Correct. Yes. So, Soham, no, in that breakdown voltage, look at this. No matter what the current, the voltage is constant. Look at this, minus 5 volts. Or whatever, minus 6 volts, that is always constant. No matter what you try to do, it will never allow you to have a voltage drop more than 5 volts. Then if you apply more voltage also, the remaining volts will be dropped somewhere else. That's what it tries to do. Okay, Soham? Sayan, no, it's not used in a UPS, because UPS is AC. It's used in DC regulations. DC regulations, Sayan. Okay, I hope this is clear. Very good, very good. Yes, another important application is LED. So whenever electrons and protons combine, electrons are free electrons. What are these positive charges? Holes. Electron jumps from higher orbit to lower orbit. What will be emitted, guys? Photons. Correct? You have studied this in atomic structure. Electrons enter into the holes. Photons are emitted. What is photon? Light. So if that energy difference is such that the photons are in the visible spectrum, you can see it, else you will not be able to see it. Thank you, Yukta, for all that love from Andhra Pradesh. Yeah. Okay, is that clear? So that is light emitting diode. You would have seen this LED lamps, LED bulbs, all the colors. So these colors are because of the photons which are emitted due to the transition. Yes, energy from the radiation. Next, photodiode. What is a photodiode, guys? Photodiode means when light falls on the diode, the conductivity changes. Have you ever gone to some nice posh restaurant and tried to wash your hands, and have you seen that the water automatically comes from the tap? How many of you have seen this? You put your hands below the sink and the water automatically falls. You don't even have to touch the tap. How many of you have experienced this? Sujal, it will be in infrared or ultraviolet or some other region. Very good. So many of you out there. So guys, you know what is the working principle of that? Oh, look at that. So many minions were there. I was wondering, where are your chats? I was wondering. Glad all the minions are there. Yes, automatic tap. It is based on this. When light falls, conduction changes and it changes some electrical parameters and it will open the wall. Alright, so when light does not fall, again it will change the parameters and it will close the wall. So it is based on photodiode. Again, a PN junction. You don't have to know exact working, but it is used over there. Cool. Very good. Okay, thank you Ritvik so much for all the loves and kisses and birthday cakes and party symbols and all those things. Alright. Sayan thought the tap was spying. No, there is no video camera. Okay, cool. Going ahead to the next one. Here is the next problem. Let's see how many of you can do this. This is Zener Diode, by the way. Okay, let's see. 2014 question. Find the currents in all the branches. Let's do this. Okay, forget the options. Okay, let's try and solve this because I want you to see how to solve this. First of all, this Zener diode has a breakdown voltage of 10 volts. You are applying 60 volts. Don't you think it would have already broken down? Yes or no? It would have already broken down. Correct, guys? So that means between points A and B, there is already 10 volts. Voltage between A and B is already 10 volts. And this diode and this resistor are already in parallel. So that means the voltage across RL is also 10 volts. Now if voltage across RL is 10 volts, I think I can easily find this IL. IL is voltage across that resistance upon the resistance itself. So voltage, how much is it? 10. What is the resistance? Think about it. The current is flowing like this. The voltage is same. 10 volts here, 10 volts here. It's already broken down. So 2 kilo ohm, that means 2 into 10 to the power 3, which will make it how much? Come on, 10 by 2, 5. So 5 milliamperes. So 5 milliamperes is flowing here. Is that understood? Very good. Now, out of 60 volts, 10 volts are dropped here. So how many volts will be dropped here? Out of 60, 10 volts are dropped here in this circuit. In this part, how much volts will be dropped? Obviously 50 volts. So isn't the current through 4 kilo ohm is also obvious? Is the voltage upon the resistance, which is 50 divided by 4 kilo ohms. How much will that be? Come on, minions. How much will it be? Come on. Very good. Everybody has answered 50. Very good. How much will it be? Come on. Yes, 50 divided by 4. Waiting. 12.5. Okay. Okay. Yes, very good. So 12.5. Very good. 12.5 milliamperes. Now 12.5 comes here, 5 goes there. How much will go here? Isn't it obvious? IZ will be 12.5 minus 5, which is 7 milliamperes. Kirchhoff's current law. 12.5, 5. How much will go here? 7.5. That's it. Done, done, done. Hello, Sasiddharth. So simple it is. So simple. That's it. These kind of questions have come. People left it because they thought, oh my god, what the hell is this Zener diode? So simple. That's the answer. You can see that. Okay, very good. Now let's come to transistors quickly. Achut, you can replay it a little bit. Okay, just replay it. Okay, let's come to transistors. Now, you don't have to know exact working of transistors and all that. Just remember whatever I tell you, that's more than enough for you to get marks in JEE Mains. That's all. Because you will learn in detail about everything about transistors if you take electrical or electronics engineering or instrumentation engineering or telecommunication sciences. So you will learn about it. For now, you just have direct applications. Now transistor is nothing but two sandwiches. Makes me feel hungry. A PN junction was P and N. A transistor is P, N and P, or N, P and N. Three things together makes it a transistor. No, Achyut, it is not there for JEE Advanced. Concentrate now. First you have to clear JEE Mains now. Okay. Very good, Dinesh. Who says you cannot pass? We will make it happen, Dinesh. Don't worry. You will and you can. So three sandwiches, rather one sandwich here and one sandwich here. So the one which has more doping is called as emitter. The one has decent doping is called as collector, and the other one is called as base. So very, very important, guys. Very, very important. Emitter has highest doping. Keep this in mind. This kind of, guys, this was a question in JEE Mains. Which of the, this time it was asked. Believe me, February attempt. If you have attended, you will know. Which has the least doping? And people are like, really? Yeah, and the answer is base. The least doping is in base. Very good, Ankit. Okay, so keep this in mind. Next, the terminals and the symbols of a transistor. N, P, N, P, N, P. N, P, N, P, N, P. Okay. N is always, the emitter is always shown bigger. The base is always shown smaller. Collector is mid-sized. Same thing, P and P. Emitter is always shown bigger. Base is the thinnest. Collector is decent. If it is NPN, this arrow mark will be outwards towards the emitter. Keep this in mind. This arrow mark will be outwards. Keep this in mind. Similarly, if it is PNP, this arrow mark will be inwards at the emitter. Write this down. You have to write it 10-15 times so that you understand it. Very good, Sujan. Excellent. Yes, very good, very good. Excellent. Okay, so keep this in mind. Okay, very good. Cool. I hope you have written it down. Next thing, always remember one more thing. Thank you, Dinesh. Yes. Once more, Indian. Acha, see, it's nothing but, I'll tell you, emitter is bigger. So N is always, in case of NPN, the biggest one is emitter, biggest one is emitter, smallest one is base, smallest one is base, medium one is collector, medium one is collector. Okay. The symbol of a transistor is nothing but show a circle. All right. Draw a line like this, show like this, show like this. That's it. Now, if that arrow mark is outwards at the emitter, that is NPN. If that arrow mark is outwards. If the arrow mark is inwards, it is PNP. I hope it is clear. Okay, I think that arrow mark was not visible, so I've just shown that arrow mark in case you are not able to see. This arrow mark was here. Maybe in your PDF, you will be able to see it clearly. Right now, it is not seen. Okay, cool. Now, next thing, very important, emitter base, keep this in mind, is always forward bias. Emitter base is always used in forward bias, okay, and base collector, all right, is always used in reverse bias. Very, very important stuff which you should know. This is because, see, transistor has 3 terminals, battery has 2 terminals. Even if you use 2 batteries, you have 4 terminals. How will you connect 4 terminals to 3 terminals? So that means one terminal needs to be shorted. You need to connect both of them so that you can connect 3 terminals of the transistor to 3 terminals effectively. I hope that is clear. Okay, so that is called as biasing. How do you connect transistors? So there are 3 different ways. One is the emitter part. All right, you take the emitter common. And you connect a battery over here. Okay, and you connect a battery over here. So you can see the emitter is common. This is called as common emitter. Okay, this is called as common emitter. If you take the emitter common. If you take the base common, what is it called? It is called common base. You can see that. And similarly, if you take the collector common and you connect batteries over here, all right, if you connect batteries over here, then that is called as common collector mode. Very simple. So basically, I'll repeat again, there are only 3 terminals in a transistor. But if you take battery, it has only 2 terminals. So you need at least 2 batteries, let's say. So 2 batteries will have 4 terminals. So what will you do? 1 terminal of the transistor, you give it as an input to 2 terminals of the battery. So basically that terminal will split so that you will get 4 wires out of 3 wires. You can see you are getting 4 wires out of those 3 wires. 1, 2, 3, 4, which can now be connected to batteries over here. So that is called as biasing. Is that clear now, Anu? Okay, so that's what is called biasing. Common emitter means take emitter common. Common base means takes base common. Very good. Yes. Very good. Excellent. Now, how does a transistor work? Briefly, I'll tell you. Guys, very simple explanation. Don't break too much of your head over this. Very simple. Imagine this is N, this is P, this is N. Okay, imagine this is N, this is P, this is N. Lot of electrons are there over here. Lot of electrons are there over here. There are holes over here. There are again electrons over here. So you know what happens? These electrons, once they see the holes, what will happen? They'll immediately jump. They will immediately jump. But remember, what did I tell you? Base is very small, very lightly doped. It is very thin as compared to the emitter or the collector. So the moment they jump, looking at the holes, moment the electrons jump looking at the holes, some of them will enter the holes, but most of them, because of the excitement, they will overshoot onto the other side. They will overshoot onto the other side. Yes, they will overshoot onto the other side, and you will see hardly any electrons go over here, and most of the electrons will go here. Keep this in mind. Okay, so that's why the current which comes from the base is very small. This base current is very small. Keep this in mind. And the collector current is very, very large. Okay, Preksha, hold on. I'm just going to complete few things. Yes. Okay, so keep this in mind. That's all I want you to remember. So most of the electrons enter the collector, hardly any electrons enter the base. So base current is very small. So coming to the transistor characteristics, let's do this. See, very important guys, if the electrons are going like this and most of the electrons are going like this, electrons are opposite to the flow of the current, conventional current. So that's it. Use that logic. Current is exactly opposite. If the electrons are coming out like this, base current is this way. If electrons are coming this way, that means collector current is this way. If from emitter side the electrons are going this way, that means emitter current is going this way. Isn't it obvious from this diagram? Emitter current is actually base current plus the collector current. Very important formula. You should know this. I hope this is clear. I hope this is clear. Okay. Next important thing. Base current is very, very small. Base current is very, very small as compared to other currents like collector current. So emitter current is approximately equal to the collector current. Very important things. Base current is very small as compared to the collector current. Keep this in mind. Very good. Next thing, if this much is clear. Okay, 2 important ratios which you should remember, beta and alpha. Now the way to remember it is beta, right? Beta is similar to B, so put B over here. That's it. Next thing, collector is a government official who is always at the top. So always put collector on the top. Collector current. Very important ratios of a transistor. Very important ratios of the transistor. Okay. Yes, this has come in JEE Mains attempt in February. Yes, collector is always on the top. Now if B comes already over here, the only thing that can come over here is emitter current. So these are again important formulas. Remember this. Yes, collector is a big position. He will always sit on the top. Collector. Base beta. So whatever is remaining will come with alpha. That's how you remember it. Yes, I told because, but somebody might be new to this lecture, so that's why I repeated. Okay, let's go to the questions, guys. Now, let me tell you, transistor is always used, like many times you will use it as an amplifier. If you have seen, there is an amplifier in your speaker or in your phone or some other musical instruments. So transistor can be used as an amplifier. How? I'll tell you briefly. See guys, the only thing you should know is this base current is very small, right? This collector or emitter current, all right, this current is very large, right? Now think about it. If beta for a transistor, or let's say alpha for a transistor, all right, it's nothing but IC by IE, and beta is IC by IB. If I change IB, then IC will change, correct? If I change IB, IC will change. But IB is very small, milliamperes, microamperes. IC is very large as compared to base current. So a small change here will create a big change here. Think about it. Think about it. A small change here will create a big change here. That means if you are giving some signal as an input to the base, there will be a big change. There will be a big change on the output side. That's what will happen. That's all. I hope this is clear. So that's the basic thing. So don't worry too much in detail. You don't have the exact circuit. Don't worry about it. In JEE, you will get direct questions. I'll tell you how it is. Okay. Now, very important to remember, look at this input side. This question came in JEE, and that's what it's going to be. If this is the input signal, look at the output signal. Output signal is bigger, but it is opposite in phase. Opposite in phase. Yes, Manmudi, it will be as important as in the February attempt, and it has a lot of weightage. It's opposite in phase because this is plus, this is higher voltage, this is lower voltage. So when you increase the current, when the collector current increases, the drop will increase. When the drop increases, the negative voltage will increase here. So it will become more negative. So that is what is important for you guys to know. So that's why it is inverted. If it is positive here, it is negative here. So keep this in mind. Yes, keep this in mind. In fact, this was the question asked in 2018. In common emitter amplifier using NPN transistor, the phase difference between input and output voltages will be 135, 180, 45, 90. This question came. This question came. Yes, Anu, it came. And the answer is 180 degrees. Because if you give this kind of a cycle, the output is like this, because if base current increases, collector current increases, so the drop increases, and the drop means negative voltage increases. So that's why it is opposite. Very good, very good. Next, here is the next question. Come on guys, let's do this quickly. Okay, so over here, for a common base mode of a transistor, the collector current is this much. For an emitter current of this much, the value of base current will be how much? Let's do this. It's not that difficult. We have to find beta, right? And what is beta? Beta is IC divided by IB, correct? Now, what else do I know? Emitter current I know. Okay. I know collector current. Acha, but I want to know base current. How do I get base current? Very simple. Base current is emitter current minus collector current. That's it. Use this formula and you will get it. IC is already given. IC is nothing but 5.488 divided by emitter current. How much is it? Emitter current is 5.6 and collector current is 5.488. Solving this, you should get the answer as 49. Check this out. Yes, that's it. That's it. That's all you need to know. The question is find beta. Yeah, from alpha also you can find beta, but this is much simpler, I feel. Okay, so that's how you solve it. Cool. Very good. So alpha and beta relationship, Sujal, you can in fact derive it. You can take it up like a small challenge. Similarly, this question was also very important, guys. Look at this. Current gain is given, all right, and it is 69. If the emitter current is this much, then what is the collector current? Okay. Simple guys. The current gain of a common emitter amplifier. So the gain of a common emitter amplifier again will be IC by IB. Okay, the current gain. Now, do I know IC? No, in fact, I want to find it out. Do I know base current? Well, I don't know the base current. So how do I find the base current? Again, IE minus IC. Use this form. Now beta, you know, beta is nothing but 69. IC is, you want to know that, you want to find that out. Emitter current is 7 minus IC. You can solve this and get it. That's it. That's it. You can solve this and get it. So, Anu, if voltage gain is asked, then voltage output will be current on the output into resistance of output. Voltage in the input will be current in the input into resistance of the input. So divide this. This will be nothing but voltage gain. This will be voltage gain. Okay, is that clear? Okay, cool. Shall we go ahead? Everybody fine till here? Yes. Solving this, you can get IC. Check this out. Solving this, you will get IC. Check this out. Okay, very good, very good. Very good. Yes, 6.9 milliamperes. Now, quickly let me tell you about gates within 5 minutes. Yeah, let's talk about gates quickly. Now, I'll tell you what, in gates, all right, it's all based on logic, and, or, NAND, etc. Why is this logic important? Because machines will only understand symbols like zeros and ones. They will not understand ABCD. Everything that you see over here is at the end of the day converted into true false, that is 0 or 1. And a computer or any electronic gadget, digital gadget, only understands 0 and 1. To make a logic work, you need these gates, which are a part of microprocessors and microcontrollers and so many other chips out there. So the most elementary operations of a complex logical circuit are called as these gates, and these are simple operations. First one is basically NOT gate. This is the symbol. What does it do? Not, negate, completely opposite. So if you give 0, so let's say this X is input, this is output. If you give false, it will make it true. If you give true, it will make it false. Truth table, that's it. So if this is 0, this is 1. If this is 1, this is 0. That's it. Is that clear? That's it. Everyone understood? Very easy guys, very easy. Very good. Similarly, AND gate. How will AND, what is the meaning of AND? For example, Pandu. Example, Pandu is rich and intelligent. Example, Pandu is rich and intelligent. Somebody checks Pandu's house, he is not rich. Somebody checks Pandu's intelligence, he is not intelligent. Is Pandu rich and intelligent? No. Gone. This is the symbol for it. This is the input, this is the output. Understood? Both should be true. You check whether Pandu is rich. Well, he is poor. He stays in a slum. You ask questions, you check his intelligence, and he is actually intelligent. Oh, Pandu is intelligent. Is Pandu rich and intelligent? No. He is not both. Next, you check Pandu's richness. He drives a Lamborghini. He is very rich. He is not at all intelligent. He is a duffer. Pandu is rich and intelligent? No, not at all. Very good. Similarly, you check Pandu's house and cars. He has a Lamborghini, he has a villa, and you check Pandu's intelligence. He is very intelligent. Then it is true. Understood? This is how AND works. This is how AND works. Very good. Very good. Understood? Very simple. Now, last one over here. OR gate. OR gate. Pandu. Okay, Pandu is rich or intelligent. Pandu is rich or intelligent. You check Pandu is not rich. You check Pandu is not intelligent. Is he rich or intelligent? No. He is neither rich nor intelligent. You see that Pandu is rich, but he is not intelligent. Is Pandu rich or at least intelligent, one of them at least easy? Yes. Or means at least one of them should be true. Similarly, yes, it's like addition and multiplication. Pandu is not rich, but Pandu is intelligent. Is Pandu rich or intelligent? One of them? Yes. Pandu is rich and intelligent. Is he one of them at least? Yes, in fact, he is both of them. That's the truth table. Yes, mathematical reasoning, correct. Exactly. Understood? Understood? So simple it is. Similarly, you have NAND. What is NAND? AND plus NOT is called NAND. AND plus NOT is called NAND. Look at this. AND plus NOT, you put a dot over there. Very simple to make the truth table, guys. Come on, let's do this. 0, 0, 0, 1, 1, 0, 1, 1. First do AND operation. Let's say this is X. This is X. 0 and 0, 0. 0 and 1, 0. 1 and 0, 0. 1 and 1, 1. Now do the NOT of it. The NOT means 0 will become 1, 0 will become 1, 0 will become 1, 1 will become 0. So this is the final output. Understood? Understood? Yes, Tejas, you can do that. Very easy. You just need to click on the link, and when that link opens, that word will come t.me, replace the t with telegram. It will work. Similarly, NOR gate. What is NOR? OR plus NOT is called NOR. OR plus NOT is called NOR gate. Very simple, just like before again. Call this as X. Call this as X. 0, 0, 0, 1, 1, 0, 1, 1. 0 or 0? 0. 0 or 1? 1. 1 or 0? 1. 1 or 1? 1. Now the NOT of it. There is a NOT. 0 will become 1, 1 will become 0, 1 will become 0, 1 will also become 0. That's the final output. So simple. Understood how to do it? Understood how to do it? That's it. That's very simple. That's it. Very good. Excellent, guys. Guys, last question, and that's it for today. Very good. So, which logic gate do you think this is? If these are two switches, which gate do you think this is? Is it NAND or NOR AND? Which gate is this? Which gate this is? XOR Achyut is exclusively OR. If both are opposite, only then it is correct. Don't worry about it. Guys, even if one of the switch is closed, think about it. Even if one of the switches closed, the circuit will be complete. Isn't that true? Even if one of the switches closed, the circuit is complete, right? Current will flow, the bulb will glow. Which gate is this? Which gate is this? Very good. OR gate. OR gate. Excellent. It is OR gate. Very good. Excellent. This is OR gate. That's it for today, guys. I hope you have enjoyed today's class. Do not forget to like this video and do not forget to subscribe to our channel. That's it for today. Now Shimon sir will be coming within next 15 minutes. Join his lecture. Quickly grab your dinner, and that's it for today. And yes, thank you for all the love and support that you have shown. I'll see you at 11 o'clock. Attend Shimon sir's class, maths class, very important, which is going to happen at 9:30. Do not forget. Okay? Bye-bye. Take care. See you.